Hi, everyone. How are you all doing? I hope you're doing well. Today, we're going to talk about the Knative Broker. Let's get started. First, let me introduce myself. I'm Grant, and I'm a Knative Eventing Working Group Lead and a Knative TOC member.
Hi everyone, my name is Song. I'm a software engineer at Google. I work actively on Knative Eventing and Knative GCP open source projects.
In this talk, we're not going to focus on explaining the broker concept or convincing you it's useful. Instead, we'll explore the history and the current state of broker implementations. We hope to shed some light on the challenges involved, the solutions people have come up with, and how one might decide which broker implementation to use. We expect most people here are familiar with Knative eventing concepts, but just in case, here are the broker and trigger definitions from the original proposal. Publishers send their events to a broker, and they expect the broker to reliably route those events to consumers who might be interested in them. On the other side, consumers create triggers to tell the broker which events are interesting and where those interesting events should be delivered. To get a bit more concrete, here are the YAML definitions for a basic broker and a basic trigger. The broker has a name, namespace, and address. The address is where publishers should send events. The trigger specifies a broker name, a filter definition, and a subscriber address. It says, if an event arrives at the default broker with the type attribute set to com.example.object.delete, then send that event to the delete processor service. The first broker implementation didn't have a name at the time, but we'll call it the single tenant channel broker for now. Its implementation looked like this. An ingress pod receives events from publishers and forwards them to a channel. The dispatcher pod receives every event from the channel, checks it against each trigger filter, and delivers any matches to the relevant consumers. For simplicity, the ingress and dispatcher pods only handle the events for a single broker, and they run in the same namespace in which the broker object was created. I'll pause for a second here to briefly talk about channels. Channel is a Knative eventing concept that's similar to broker, but doesn't support filtering. It's meant to be a simple interface to an external messaging backend. Publishers send events to a channel's address, just like broker. In this diagram, that's B1-channel. To receive events from a channel, we create a subscription object, which is like a trigger, except it doesn't have a filter. Each subscription receives every event that's published to a channel. The channel keeps track of event deliveries and failures to make sure that each event is delivered at least once to each subscription's consumer. Now back to the broker. The publisher delivers an event to ingress address B1-broker, which forwards it to channel address B1-channel. For every trigger, there's a matching subscription that delivers events to the dispatcher at a trigger-specific path, /T1, /T2, etc. The dispatcher filters each event for the trigger path it came in on, then if it matches, delivers the event to the consumer and reports success or failure back to the channel. You can see in this example one of the challenges of this and other broker implementations. I'll call it over-delivery. 3 red dot events are delivered to the dispatcher, but only one makes it to a consumer. The other 2 deliveries are wasted resources, and that waste grows as the number of triggers grows. The single tenancy of the single tenant channel broker was also a resource efficiency challenge. Since it didn't have scale to zero autoscaling, the pods for ingress and dispatcher were always running, even if the broker was idle. For clusters with many idle brokers, this was a lot of pods doing nothing but taking up space. So, we decided to replace the single tenant channel broker with the multi-tenant channel broker. Its implementation is similar to the single tenant channel broker, but the ingress and dispatcher workloads are shared by all brokers in the cluster, and they run in the system namespace. Autoscaling to zero isn't so critical anymore because our minimum footprint is now 2 pods per cluster instead of 2 pods per broker. And because all brokers share the same infrastructure, the aggregate resource efficiency of all brokers can theoretically be better than the same number of single-tenant brokers. The event flow through the multi-tenant broker is the same as the single-tenant broker. All events sent to a broker go to a single channel and are delivered once per trigger to the dispatcher. The biggest difference is that publishers use a URI path to send events to a broker instead of a hostname. Note that the over-delivery challenge isn't solved by this implementation. And because the data plane is shared by all brokers in the cluster, there's a risk that a single noisy broker will starve the other brokers of resources. This is a trade-off. Multi-tenancy allows for better resource efficiency, but isolation is harder to achieve. Now I'll hand off to Song to talk about the other brokers in our Knative ecosystem.
Thanks, Grant. First up is the RabbitMQ Broker. The RabbitMQ Broker has a very straightforward design. In fact, you can find one-to-one mappings between RabbitMQ components and the Knative concepts. Each Knative Broker object is mapped to a RabbitMQ exchange with an ingress service as the adapter. Quite similarly, each Knative trigger object corresponds to a RabbitMQ queue and a dispatcher. Recall that in Knative Eventing, triggers express interests to events by filtering on event attributes, and this is implemented in RabbitMQ using headers exchange and bindings. First of all, event attributes are translated to message headers. A binding then connects a queue for a trigger to the exchange by applying filter attributes as binding arguments. In RabbitMQ Broker, each broker has its own ingress deployment and exchange. Each trigger has its own dispatcher deployment and queue. The ingress and dispatcher live in the user's namespace where the broker and trigger were created. This is very similar to the single-tenant channel broker that Grant just talked about earlier. Since there is no resource sharing, the resource usage is something to keep in mind if you consider using the RabbitMQ Broker, especially when you need a lot of brokers or triggers. There is no auto-scaling on the ingress currently. However, on the dispatcher side, KIDA is used to scale dispatchers. Currently, it does not support multiple replicas, but it does support scale to zero. So if most of your triggers are idle, you're still fine in terms of resource usage. Next, let me walk you through how event flow in RabbitMQ Broker. The publisher sends an event to the broker ingress endpoint. The ingress translates the event to a RabbitMQ message and publishes it to the corresponding exchange. A queue is created for each trigger and connected to the exchange via a binding. The binding filters the event based on message headers or event attributes. Finally, if the event passes the filter, the dispatcher pulls it from the queue and sends it to the consumer. In RabbitMQ, queues can share a single message store. Therefore, there is not a lot of duplicate storage overhead by creating a queue per trigger. And besides, The filtering happens within RabbitMQ, and therefore there is no wasted delivery of events from the RabbitMQ to the dispatcher if they don't even pass the filter. Next, let's talk about the Kafka Broker. Similar to the multi-tenant channel broker, the Kafka Broker uses a multi-tenant shared data plane. The ingress is sliced to serve multiple brokers by sharing a path. A Kafka topic is created for each broker, like a channel is created for each broker in the multi-tenant channel broker case. A multi-tenant dispatcher is responsible for pulling events from Kafka, applying the filter, and delivering the events to the consumers. If we look closer, the thick arrow can be split into multiple ones, each representing a consumer group for a trigger. An interesting fact of the Kafka broker is that the data plane is implemented in Java because the Kafka Java client is better supported than the Go client. There is a single shared data plane that runs in the system namespace, and it can be deployed by a YAML file. There is no workload running in user namespace where brokers and triggers live. As of today, there is no scaling strategy implemented. Let's take a more detailed look of the event flow. The publisher sends an event to the endpoint of the target broker, which points to the shared ingress. You'll notice that the broker endpoint is a path of the ingress. The ingress sends the event to the corresponding Kafka topic. The shared dispatcher pulls event from the Kafka topics using trigger-specific consumer groups. It finally sends the event to the target consumer if the event passes the filter. Now let's move on to the GCP Broker. The GCP Broker uses Google Cloud PubSub as the messaging backend. It is similar to Kafka Broker on the ingress side, where it uses a shared multi-tenant ingress, and a PubSub topic is created for each Knative broker. A unique design aspect of the GCP Broker is that the dispatcher is split into separate fanout and retry stages. For each broker, fanout pulls events from the corresponding PubSub topic via a pull subscription only once, and for all triggers. It then attempts to deliver the events to all matching consumers only once. For each failure or timeout, the event is published to a trigger-specific retry topic. The retry stage periodically pulls events from those topics and attempts to redeliver to the consumers. What motivated this design is the PubSub pricing model. In PubSub, users are billed by the overall ingress and egress traffic, while there is no storage cost. Therefore, it is important to avoid duplicate methods deliveries from PubSub for multiple triggers in the happy path. And while in the error path, when there is no storage cost for publishing failed events to multiple retry topics. While multi-tenant broker designs are great at resource sharing, a globally shared data plane reduces the flexibility to apply curated configurations and auth scopes for different use cases. For example, an operator may want to apply different resource quotas for brokers owned by a specific team. GCP Broker solves this problem by allowing multiple data planes, while each data plane is still multi-tenant and can still serve multiple brokers. Broker cell is a customer resource which manages resources for a multi-tenant broker data plane. A broker cell can be created and configured by an operator upfront, or a default broker cell can be created automatically by the control plane. The default broker cell is only created when there is at least one broker. In this diagram, broker 1 and 2 are assigned to the default broker cell, while broker 3 is assigned to a customer broker cell, which has an isolated data plane than the default. Note that the ability to assign brokers to non-default broker cell is not fully implemented yet, but this is a low-hanging fruit. The GCP broker currently uses HPA for auto-scaling. Other scaling mechanisms, such as KIDA, is under investigation. Back to you, Grant.
Thanks, Song. So what can we take away from all this? Well, if you're a user wondering which broker to choose, ask yourself a few simple questions. Are you more concerned about resource isolation or resource efficiency? Are you interested in using channels? Do you prefer Kafka or PubSub? There are no right answers, and each choice has its own trade-offs. But we hope you can find something that fits your needs. If you're a contributor that's implementing a broker, here are some basic principles to keep in mind. First, every messaging system has something it does really well. Try to optimize for those strengths. Second, your broker should not be significantly slower or less efficient than using the messaging system directly. To achieve this, use the messaging system as little as possible. Filter uninteresting events early and avoid over-delivery. Third, be aware of the trade-off you're making between efficiency and isolation when you choose a multi-tenant versus a single-tenant data plane. Finally, if anything we talked about today was interesting to you and you'd like to learn more, or just dive in and start contributing, we'd love to continue the conversation. Join the Eventing channel on Knative Slack, or head to one of these GitHub repositories to learn how you can get involved. Thank you everyone for your time.